welcome to our third day of this exciting workshop. And I am glad to see finally that there will be a talk without the S word.
Oh, no, I added it in there.
Okay, I mean, I looked at your work, at your abstract, there was no S word in it. So I thought that all of you thoroughly merited a break from that. Okay, so our speaker for our first talk today is Max Willsey, who is a professor here at Berkeley since September. Am I right?
Since the coming January.
Oh, okay. But I mean, morally you are.
Yes, morally. I'm physically here.
Thank you very much.
Alrighty, let's get started. Thanks for having me. So this work that I'm going to talk about today is joint work with my collaborators during my PhD and postdoc at UW, which include Remy Wong and Zach Datalog, both of whom are here. And we're going to be talking about E-graphs, which is a data structure you may not have heard of, and we're going to do so in 4 ways. And this is going to sort of document my journey from being a PL and compiler optimization, PhD student and postdoc, and sort of slowly getting dragged by Remy mostly into the world of databases. So I hope you will find some interesting connections and maybe some applications of this work along the way. All right, so the 4 ways we're going to talk about E-graphs today is the first one I'm going to talk about it in the sort of conventional way as a data structure, and we'll talk about the various ways in which they're used. But then, as I said, I'm going to sort of talk about this journey that we've taken in sort of converting E-graphs or encoding them into Datalog in various forms. I'll talk about first an unsuccessful attempt, and then a successful attempt with some big caveats. And then I'll talk about some ideas that I have, and this is where the S word may come in, to sort of undo some of those caveats and get back to good old Datalog. All right, but first some motivation, like why are we talking about E-graphs? What is this data structure used for? So whether I come from the compiler optimization world, and a fundamental thing that you want to do in that context is transform terms. You're doing term rewriting. So here's a program, a simple arithmetic program, a times 2 divided by 2. And we might want to optimize this to A using some identities. Or maybe we have these 2 programs and we want to verify that they are equal. Sort of the predominant technique that you would use to do this is term rewriting. And the way that this works is you have a list of identities that depends on your domain. And the trick is you want to come up with all the identities that you can, because some of them are going to be useful and some of them are not going to be useful. So over here are, and we'll see this in detail in just a moment, these are exactly the identities that you would need to sort of do this transformation. But I can, of course, come up with a lot of true things that I could say about sort of arithmetic here that are not so useful. Or in fact, not only just not useful, but are sort of will prevent me from doing the optimization that I want to do. So let's see what the happy path looks like. I sort of apply these identities from left to right in order. Oh, yes, please.
In your previous slide, you speak about transformation, that is the yellow arrow. To do this, you use equality that say you can see as a double arrow some way.
Yes.
There is some connection, the fact that on the useful equation, there is a double arrow, and on the yellow one, there is an arrow only one direction. Yeah?
That's right. So yeah, so this is exactly right. I am sweeping a little bit of this under the rug. For these identities, you can think about them as double arrows, but of course there are transformations where both directions don't hold, and we'll get to that a little bit later. Okay, so let's look at the happy path. Here I'm only going to sort of invoke these arrows in the one direction. So first we sort of reassociate the multiplication with the division, and then we can see, aha, we can perform a cancellation, fantastic, and then we can do another identity, and we've optimized our program, fantastic. But let's look at some of the pitfalls in this term rewriting technique. Sort of the most insidious one is, I think, this first identity. So this says that if you're multiplying by 2, instead you might want to do this as a bit shift. This is a classic sort of compiler optimization. This is really fast, and this is can be much slower. So in some sense, locally, this is always a good idea, right? You've taken an expensive operation and you've turned it into an inexpensive operation. So in fact, we're going to do just that, and hooray, we've optimized our program. But the problem is, in doing so, we've made a locally optimal choice, and we prevented ourselves from seeing the sort of globally optimal optimization here, right? By taking this turn, we can't see that the 2's line up, and then we can cancel them. Other sort of problems are you can get stuck in various kinds of infinite loops. So of course, if we want to reason about commutativity, we have to be very careful because you can, of course, commute things back and forth and end up right where you started, and that's not very useful. And likewise, if you apply expansive identities in the wrong direction, you can wind up creating terms of arbitrary size, which again sort of gets you stuck in your term rewriting process. And the last thing I want to say about this is that in this sort of contrived case, these are all bad ideas, but it's not very difficult to come up with optimizations that you might want to do where these are in fact critical. These are exactly the optimizations that you want to do. So the question when you're writing a compiler, one of the fundamental things is, which transformation do you apply at which time? Turns out this is a really tricky question. There's a lot of smart people that have taken various attempts to answer this question. And we've sort of sidestepped this question with a technique called equality saturation, which allows you to apply all of these transformations simultaneously. Now, it has a cost that we'll get to in a second, but it does allow you to sort of sidestep what's called the phase ordering problem. You don't have to worry about committing yourself to a wrong decision, a wrong transformation. All right, and the technique is called equality saturation, and the data structure that powers it is called egress. Yes?
Sorry for so many.
No, please.
I'm wondering, is the framework that you have considered is confluent in the sense that there is only one, let's say, normal format that you can reach for the transformation, or you can arrive to different, not more transformed piece of information?
Yeah, so I mean, the question is about sort of confluent term rewriting systems, and like I said, when it comes to term rewriting, of course, there's a rich history in terms of you can complete your term rewriting system. If you have a confluent term rewriting system, you could sort of you could just go, and you can have confidence that you won't take a wrong turn. So here we are, the method that we are using, we don't want to have to manipulate or constrain the identities that we have. So we want to admit term rewriting systems that are not terminating or not confluent. We want to still be able to do something with them. All right, so let's actually look at what is the eGraph, what is the data structure. All right, and so if you're familiar with the memo table data structure used inside the Cascades query optimization framework, some of this will look a little bit familiar to you, despite the fact that they have sort of independent intellectual heritages. Okay, so what is an eGraph? It consists of two parts. It has E nodes, which are sort of the nodes in your program AST, and they're grouped into E classes, equivalence classes. All right, and if we want to optimize a program, we're going to start out with a sort of boring-looking eGraph. This eGraph doesn't record any identities because each E node is alone in its E class. Right? We haven't really done anything interesting yet. All right. First, I want to define this notion of representation, which again is boring now, but it will get more interesting in a slide or two. We say an E-class represents a term when you can sort of follow these edges and find that term inside the eGraph. Again, that seems boring, but one important thing to note is that inside our eGraph, the parent-child relationship, E nodes point to entire E classes. They don't point to a node within that class. And this sort of captures the substitutability principle, right? If I'm an operator, I don't care, if I have choices on which of my argument are. If they're equivalent, I don't care which one I take. But that's the whole point of them being equivalent. All right, so let's make this a little bit more interesting by growing our eGraph. Let's apply our problematic rewrite. Okay, this is the one that's a good idea locally, so we want to do it. But in this particular case, will prove to be a wrong turn. So the way I'm going to apply this rewrite to the eGraph is I'm going to look for instances of the left-hand side where x is a variable. And in fact, I found one right here. So if by substituting a for x, I can see that, hey, I've represented this term here. Okay? And where in term rewriting, I would replace this subterm with the instantiated right-hand side. Instead, I'm just going to add the instantiated right-hand side into the same E class. Right? And so this is a monotonic process, meaning that the old version, the sort of transformed away from version, is still represented within this E class. And in the same E-class is, of course, the right-hand side of the transformation as well.
So can I,
Yes, please.
so you have a bounding box around two operators,
Yes.
but not the descendants of them. So this means conceptually the operator, you just link in this visual representation to the operators, implying that actually everything that's descendant from them is part of this equivalence.
Yes, I mean, so those are distinct things, right? You know, they have some similar arguments, but I want to be careful not to equate 2 and 1 in this context, right? The children of these arguments, right? So I need to be careful that I apply the equivalence only at the sort of root level of my match here.
I see. So the box means actually these two subtrees rooted at these nodes are equivalent. That's what this means.
Yes, it means that all of the programs represented in this E-class, here we can see that we represent exactly 2 programs, are considered equivalent. Yes?
Do we try to make them irreducible in a sense that, like, if I add another rewrite that also uses the one node, I would always try to reuse an existing one?
Exactly. So that's one thing that I sort of snuck past. In fact, even in our boring AST, we are doing sharing. And once you start making equalities, the sharing becomes very sort of prolific. It compacts the data structure quite a bit. Good question. OK, so now this E-class with 2 nodes in it represents 2 programs. That's all well and good, but that's not very exciting compared to the fact that this notion of representation propagates up. This is sort of the magic of the data structure. So this E-class up here, despite the fact that we haven't touched it, and it only contains a single E-node, now represents 2 programs. Okay, and that's because its one of its child E-classes represents multiple programs. And so you can sort of see if you chain up a ladder of E-classes that have multiple things in them, you're going to start representing exponentially many programs in a very compact space. And so, you know, this is sort of ... here. We can apply the rest of the transformations. Notably, we can apply this transformation that is still looking for the multiplication that, if we did this in a destructive way, would have been deleted, right? Like we would have gotten rid of this multiplication. So it turns out we can actually still do this rewrite, and we can do the rest of the rewrites. And we can arrive at our conclusion that our original program, which was sort of this division node, is in fact, it winds up in the same equivalence class as A itself. So that's great. That means we've performed our optimization. Another sort of subtle thing that is a little bit difficult to notice with all these arrows going around here is that we have a cycle in our E-graph. So this E-graph actually represents an infinite set of programs. And so you can see this multiplication node, its left child, is in fact the same E-class that contains it, which means that not only does this E-class have our original program and our optimized program, but it has all of this, you know, this whole set of programs, A times 1, A times 1 times 1, A times 1 times 1, and so on. All right, and you can actually proceed with this operation until nothing happens. In fact, when you add equalities, many times the data structure shrinks. Right, and you can get to a point, because you're doing this compaction, that you're reusing nodes as you find them. You can get to a point where you keep applying these rewrites and nothing happens, and we call this saturation. This means that you've learned everything that you're going to learn, everything that is derivable from the identities that you've been using to rewrite. All right, so what we've done so far is basically verification. We've said, like, hey, you know, this thing is equivalent to this thing. But when we're doing optimization, the question that we want to answer is, hey, I have an input program. Give me the best output program. So this is sort of the final piece of the puzzle. And this is a phase that we call extraction. So I want to say, hey, my original program I know is somewhere in this E-class. Give me the best program that is in this E-class now. So like I said, it represents a ton of programs. We want to make sure that we don't want to extract A times 1, because that's not optimal. We want to extract A. So we want to pick the one with the smallest, cheapest size. We use an algorithm that turns out to be from Don Knuth in '76. It's basically shortest path over hypertrees. It's a very simple bottom-up algorithm. And Al, I apologize. Here's where the S word comes in. One thing that we've discussed during this workshop is that, in fact, you can view, for any particular E-graph, it induces a set of polynomial equations. And if you just solve this in the min plus semi-ring, you actually get the cost of the cheapest term inside each class. Did you have a question back there?
Yes, you say the best, the short, what is the idea of finding the best?
Yes, that's a great question. So we've sort of, for this algorithm, for the Knuth algorithm, which is the same as this, we are using the shortest tree size. Turns out in a lot of applications, you care about the DAG size, meaning that in your extracted program, you're allowed to sort of let bind variables and only count their cost one time. That's an NP-hard problem. We have some encodings into like ILP and MaxSat, but it's very sort of apparent that it's NP-hard.
I'm missing something fundamental
Yes.
about what is in the theory that allows you to make the inference that the programs are equivalent. How do you deal with that? I mean, what do you have in there?
So from
Equational theory?
yes, so from this system's perspective, all of the rewrites that are given are axiomatic, right? So it's equational reasoning modulo the axioms that are given to the system. So those are completely trusted. You can easily wind up in a situation where you're proving 1 = 2 if the rewrites are unsound.
Are the axioms also equational, or do you have semi-conditional equations? What do you allow in there?
So far we've only discussed equational ones. We do allow for conditional ones, but we haven't built up the mechanism for that yet.
The problem of deciding that these two programs are equivalent, right? Somewhere.
Yes. So you can use this as a sort of semi-decision procedure for the word problem or program equivalence. It doesn't terminate, so that's where you, or it may not terminate. So that's where this is.
Thank you.
I don't know if is saturation a necessary condition for the extraction phase to work properly?
Certainly not.
Yeah.
So you're basically under approximating the set of provable equivalences, and you may never arrive at it at the complete set. So you can always, and in fact, in practice, because termination is very frequently never going to happen, you have to stop early. Yes. Right. Okay, and so that's the framework that we call equality saturation. We could put it all together where we take in our initial program that we want to optimize, we chunk it into an E-graph, and that was that sort of boring AST-like E-graph that we saw at the beginning. And then we turn the crank. We do these rewrites. We find the left-hand sides, and we add the right-hand sides into those E-classes. And then we perform extraction. And we get our optimized term out. All right, whoopee. So the great thing about this approach is that it turns optimization, which is this, or program optimization, which is this, there's all these complicated choices on which rewrite to apply and which rewrites are even emitted, into sort of a two-phase problem. One is which I'll hopefully try to convince you, is basically performance engineering. It's a Datalog problem. This is actually more or less running Datalog. And the second part, extraction, is a combinatorial optimization problem. When the cost function, like the question, is simple, we can do that simple Dijkstra's algorithm. And when it's not simple, we have to resort to much more heavyweight techniques. So that's basically all I will say about this combinatorial optimization phase. And I want to dive in a little bit further to this do rewrites phase and hopefully convince you that Datalog is the right sort of execution mechanism to make this go fast.
So one quick question about the kind of equivalences that we could support with equality saturation, right? There might be some equivalences that introduce new variables, right? Is this allowed? Because then maybe I could see that you're not guaranteed to terminate.
Exactly. It's not only allowed, it's essential, right? Even consider associativity, right? X plus Y plus C goes to X plus Y plus C. And from the Datalog perspective, Y plus Z, it needs to be existentially bound in the head, right? You don't know that Y plus Z existed beforehand, right? So absolutely, your termination is completely out the window as soon as you have, sort of modestly interesting rewrite systems.
Since the operator that you use can be not only to represent, let's say, classical algebraic operation, but would be also operation of some languages or something like that. I'm wondering if you consider some relation to your framework to graph transformation and graph grammars, And also another question is sometimes you are not looking for the best or shortest form of the formula, but to a sort of a normal form that could be not the shorter one.
Mm-hmm.
So it's different optimization goal.
Right. So in terms of working with graphs and doing graph transformations, that is definitely supported in this framework. And I think that will become more obvious once we encode this in Datalog, because as this was conventionally posed, it was sort of unnecessarily restricted to tree-based transformations. But once you encode this into Datalog, you can do the graph transformations just fine. In terms of extracting a normal form or finding a normal form, I think you've hit the nail on the head. The problem is coming up with a cost function that, when minimized, gives you your normal form. And that is, could be very difficult depending on what your normal form in question is.
I mean, I apologize to Stefano for making this remark right after your question, but I would like to encourage you, Max, to remember that we also have a half an hour for free discussion after the second talk this morning. And if you feel that some questions are better addressed to them, please and blame me.
All right, blame Val.
And do that.
All right, well then let's get going and get to the Datalog part. But first I want to explain just a little bit about how mechanistically this do rewrites part worked before the sort of Datalog revolution. Okay, so this phase is called E-matching, and you can think about this as pattern matching modulo equality. So here's another E-graph, and we don't have to it's sort of meaningless, it's very contrived. And let's say we are looking for the pattern F alpha G of alpha, right? And so this is a nonlinear pattern, meaning that we've got alpha used 2 times, and they better agree in every one of the matches that we find. So what is a match? The result of E-matching this pattern is we want to get substitutions that map the variables in this pattern to E-classes in our E-graph, such that when you sort of instantiate them, you get terms that are represented in the E-graph. Right? In particular here, we don't want to get f of 1, g of 2, because that's, that doesn't match our pattern. All right, so how is this implemented before? Here's just an example of a pattern match. All right, so let's implement E-matching. It follows, it's a top-down backtracking algorithm. If you've ever written a pattern matcher, it looks very similar to that. And the E part turns out to be not that difficult. You just loop. All right, so we're looking for our pattern f of alpha, g of alpha. Well, first let's go over every E-class. Not too bad. Now, in that E-class, let's just find all of the F nodes. Easy peasy. Once we have found an F node, we can start building up our substitution. You can think about this as this is the substitution that we'll eventually return. And so in the substitution, we want to record that alpha maps to the left-hand child of the F node. And we also want to write down the root of the pattern match. We want to record where the match occurs. We're not done yet. We have to check that the rest of the pattern matches, right? We want to make sure that the G of alpha also lines up here. So let's loop over the G nodes in the right-hand child. And we have to do one more check here. We have to make sure that, hey, the child of the G better agree with that left-hand child of the F. That was the whole point of using a nonlinear pattern. And if that's indeed true, then we could yield substitution. So these data structures, E-graphs and E-matching, are in fact a really important part of how SMT solvers work. E-matching is one of the procedures used to instantiate quantifiers inside of these tools. And this is more or less the algorithm that has been used since forever to do quantifier instantiation. Now, for this crowd, I want to point out something that is sort of suboptimal. Well, no, it's very easy to show that this is n squared time in this E-graph, where I've sort of stacked everything up to be n wide. We just have 2 loops over these nodes. But if you sort of look at the greater structure, it's obvious that there can only be n results. Right. So if we think about this from a data complexity perspective, it's very unsatisfying. So this is basically, I guess, what I just said. The existing implementations, they are backtracking, and they do have a suite of complex optimizations that more that are sort of getting close to what we might think of as query optimizations, but are falling short in many important ways. The biggest one that they fell short with were on these so-called equality constraints. So if you're matching a non-linear pattern like f of a and a again, there was no optimization based on that, right? It would just wait until it matched the whole pattern, check, and then proceed. And there are no data complexity results. Everyone has always known that e-matching is NP hard in the pattern size, right? But if we think about this as sort of answering a query, that's obvious and uninteresting. We want to know, how does it grow in the e-graph size? All right. And the last thing I want to say, we talked about syntactic operations over these e-graphs. But if you come from a program analysis background like myself, there's more than syntactic reasoning, right? Sometimes you want to consider the semantics of the program in the e-graph. If you want to do arithmetic, for example, constant folding, you're going to need a lot of syntactic rewrites to make that happen. You might want to actually look at interpret the values in there and do some semantic reasoning. There's all sorts of program analyses that we can actually do inside the e-graph using the framework called e-class analysis that we came up with to represent this. And I want to speed through this a little bit because I want to get to the Datalog portion. We come up with this framework called e-class analyses. And just a brief example of how that works. Say we wanted to do constant folding over the e-graph. The way that you might think of doing it is you attach an optional number to each e-class. And then as new e-nodes come in, you evaluate them. And when equivalences are made, you merge the two options, right? So if we're building this e-graph from the bottom up, we obviously know 2 is equal to the constant 2, and we don't know anything about a yet. And of course, this means we can't say anything about multiplication or division yet. But if for some reason we learned that a is equal to 2, then the analysis should be able to respond to this new equality and react all the way up and say, aha, now we can actually say something about the multiplication node and likewise the division node. All right, so we have this framework called the e-class analysis. We framed this in terms of semilattices, where you attach one fact from some semilattice to each e-class. And there's a pretty simple API to create these. The important part here is that when you combine analysis values according to an equivalence merge, that has to obey the lattice laws. All right, and I'm going to just speed past a little bit of this. The intervals example is very neat, but I want to get to the Datalog portion. Okay, so everything that I've said up to now basically documents the state of the art as of 2021, right? We wrote this paper that was like, hey, e-graphs and equality saturation, it's a really powerful technique. People are using it for program optimization, query optimization, and that's all well and good. The challenges are we need to make it go faster. It's made program optimization to this sort of search problem. And we need to if you want this to scale, you need to make that search go as fast as possible. So this is where we're going to look to Datalog to sort of speed up that critical e-matching phase. All right, so we know that our e-matching problem looks like answering a query, and we know that the database people know how to answer queries. So let's take a first crack at trying to encode quality saturation as Datalog and see where it falls over. So again, why would we want to do this? If you sort of think at a high level, equality saturation is a sort of monotonic process, right? The whole idea is that you're adding equivalences and you're never removing them. That was the sort of, we don't want to do destructive rewriting. And we know that answering the e-matching, while it's the bottleneck, has this sort of query answering-like behavior, right? So, and this is honestly was enough to get us started, right? We were like, hey, this sort of feels a little bit like Datalog. Let's see if we can just sort of smash it into this framework. All right, so how would we do this? Well, obviously, if we want to do it in Datalog, we're going to need some sort of tables and schema. So let's just take a crack at it. So here's a very simple, we don't even have an e-graph yet. Let's just start with terms, right? So I have plus A plus BC. And the encoding that we're going to start out with is just sort of flattening for each function symbol. So for here, we only have the pluses. We're going to have a table where the there are n+1 columns where n is the arity of the function, right? So the first two columns are going to be the inputs to each function. So each row is going to be a node in our AST. So I think this one corresponds to this one, and this plus corresponds to this row. And we need to sort of make up a value name for the final column, right? So we're going to say that this plus BC, we're going to name it BC. And that way we have some token to refer to in the upper plus. And likewise, we're just going to name the value of that one ABC. Okay, so this is just a flattening of this tree into this table. Notice we don't have any E classes or anything yet. Well, let's just start trying to do some rewrites. Let's see what that looks like. Our working example has sort of been associativity of plus. So let's see how we might write this down in a Datalog-like thing that has these terms in them. Well, so okay, the rewrite it goes left to right, but because we're doing Datalog, I'm going to do it right to left. So let's just look at the query portion, right? We want to look for things that are an addition with another addition on the right-hand side. All right, so what does that pattern look like? So this is the sort of top level here. We want an addition where I'm going to bind x and yz. I'm going to sort of suggestively name this yz. And recall, I want to also remember where this addition is occurring, right? So we're going to name the sort of output of this addition as root. And I also want to make sure that this yz is also an addition, right? So I'm going to say another tuple in our body is going to say yz better be an addition of x and y. All right, so we've got the query. Now we need to figure out what the head of our Datalog rule looks like. And this is where we need basically TGDs. So I've underlined and bolded the two things that are need to be existentially bound in the head. You'll notice that these are not bound by the body. One thing that is tempting is that because root is the sort of value of our, this thing that we're trying to rewrite, it's very tempting to put root here. But we can't do that because these are existentially bound. We don't get to name this because we're going to be using an implementation of Datalog with algebraic data types, right? So when you put these ADTs in the head, you only provide the inputs and you receive the output. And it's going to do this sort of hash consing for you. It's also worth noting that we don't have sort of full existentials. The existentials always appear in this sort of position that in this final position that could be resolved from a functional dependency of the inputs. Right? This is what it means to be an algebraic data type. Right? Your output is determined by your inputs. Okay, so yes, please. Yes.
I was going to ask about functional dependencies.
Yes. So we're trying to sort of bolt on, and there have been other works that have done this as well, basically the theory of algebraic data types into our Datalog, right? And so the way that we are implementing this is that all of our tables are in fact backed by a map, right? And indeed, right? And so that map is going to not only ensure that we have consistency across sort of calls to the input, but it's also going to be the thing that gives you this existentially bound variable. Okie dokie. So we just did something, but where was the E, right? Like we did pattern matching, and I said, it was tempting to put this root here, which would have actually recorded an equivalence, but we didn't do that, right? So what we've actually done is we've just, added another, addition term to our database, and we haven't recorded any relationship between the input and the output, which is sort of the whole point of equality saturation, right? We need to add equalities. So what are we going to do? I mean, the egraph is an equivalence relation, right? So we need something in our Datalog that actually says something about equivalence. It's also a congruence relation, but we'll get to that in just a moment. And we also need to do our pattern matching module equivalence. So not only did we not add any equivalences, we didn't read any, which is, again, the whole point of doing e-matching. So we need to do something about this for this encoding. And the really important thing here is that equivalence is user extensible. All right. So think EGDs, right? this notion of equivalence is something that the user is going to be building up dynamically sort of at runtime. So how are we going to do this? Well, our first stab was, well, equivalence relation is just a relation. It's symmetric, transitive, or reflexive. We can write down all of those things as Datalog rules. So let's just do that. We have an additional binary relation in our encoding, and we need to ensure that all of our joins become joins modulo equality. Right? This is what it means to do e-matching. Right? So if we wanted to do this eq join across this y variable, we now need to split those two variables and join it across our equivalence relation. Right? This makes sure that every time we do a join, it's respecting new equalities that might appear from the user. Fantastic. So this is, in fact, sort of the ingredient that we were missing. Right? So if we wanted to do this example, associativity of plus, we can get there. We don't have to fully go through this example, but the one thing I want to highlight is that we are, in the body, we have an equivalence. We're joining across equivalence to actually do the e-matching. And in the head, we have an equivalence as well. I think this is a typo. This is supposed to say eq of root and root 2. That's, sort of what was the whole point. One interesting observation to be made here is that nonlinear patterns, which are in fact very interesting ones, this one is not nonlinear. So imagine we had an x here. These flatten out to cyclic patterns, right? So pretty simple patterns will very quickly become pretty complex Datalog queries. And the final ingredient is the egraph is a congruence relation, not just an equivalence relation. But that's no problem for this encoding. We can just write the rule. Again, it's a sort of a pain in the butt to read, but this more or less says exactly congruence. You're saying, hey, if there are two pluses where all the inputs are equal, it better be the case that the outputs are equal too, right? Like that's what it means. That's the definition of congruence. All right, we did it. We encoded equality saturation in Datalog. The problem is that this doesn't work. It's way too slow, and I hope I want to try to get across the main things that make this encoding too slow, because it's very tempting to do this. The biggest, or one of the big things, is that the equivalence relation will blow up to n squared in size, right? If you have n things, or for every e class of size n, you're going to record n squared equivalences. So that's a huge problem. There are some tricks that we tried to do to fix it, like some folks from the Soufflé Datalog system. You can implement, and of course, in code, you can use a union find to represent an equivalence relation in linear space. And they have such a trick that you can have basically a union find to represent a binary, an equivalence relation in your Datalog program. So we were super excited about that because it does give you that compact representation. The problem is, for that implementation, it's difficult to join across it. So it turns out if you join across that equivalence relation, it ends up basically expanding it to the n squared size table anyway. So you've lost your compaction. Another tempting thing is to use subsumption. So if you're familiar with subsumption, it's basically a technique in Datalog to remove tuples in some sort of way that respects monotonicity. And the reason we were excited about this is that the egraph under the hood is actually canonicalizing things. So it's ensuring that there are no duplicates, and that when equivalences are made, you only hold on to a canonical representative. And so this basically means removing all the non-canonical representatives. But unfortunately, the Datalog implementations of subsumption, as of right now, are too slow. There's a student at University of Washington named Yi Hong who has basically documented all of these failed attempts in his master's thesis. It's quite interesting. All right, so how are we going to make this work? How are we going to do egraphs as Datalog and make it actually usable? So again, what was the problem? It was something in the equivalence relation. Not only it was too big, it was n squared, but we need to be able to join across it in an efficient way. Right? N squared size, et cetera, et cetera. But more importantly, the fact that we weren't canonicalizing is something that took us a long time to realize, and is really the key thing that makes the egraph go. So hopefully this picture will relate what happens if you don't canonicalize. So here is a picture of a sort of uncanonicalized egraph, right? This is actually, in the old egg or egraph as a data structure, this is sort of malformed. We would consider this malformed. For the following reason. I've labeled these GE nodes with G1, 2, 3, 4, but those are only for our purposes. Consider these to actually just be the same operator G. All right, so the thing to observe here is that these two G's are not only equivalent, but are identical, right? They refer to the same E-class, right? And you can imagine this sort of goes on and on, right? So this is an E-graph that has not been canonicalized. So because if you did canonicalize these two G nodes, they would become syntactically identical and would be deduplicated. But let's suppose we haven't done that yet, all right? If we don't do that and we are looking for some pattern, let's say we have some pattern f of g of x, all right? Well, what's going to happen? We can still E-match that over this sort of malformed E-graph, but we're going to get combinatorially many results, right? To find f of g of x, I could go this way, 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 all the way down, right? And we can see that, sort of scaling with the height of this E-graph, this blow up is exponential, right? Whereas if we just canonicalized, it would just be a single result, right? So we've really missed something by not including this in our Datalog encoding. So the answer is that we have to canonicalize, right? And so this is where if you like Datalog, you should turn away, because we're going to do some really, really nasty bad things. Well, we're just going to do what the E-graph does. We have a union find to record the equivalence relation. The nice thing about a union find is that you get this function called leader of x. So if you want to figure out whether two things are equivalent, you can, in fact, just look up their leaders and say, hey, are they the same thing in this union find? And so you can answer this question very, very quickly.
Sorry, what do you mean by leader?
So the union find is implemented as a forest. Leader is basically what is my current root in the union find data structure, right? Of course, if two people have the same root, they're in the same subtree, so they're equivalent. All right. So the way that we would do this in eGraph land is the eGraph is basically a data structure for congruence closure. That you implement the congruence closure algorithm. We're not going to get into it here, but it's not that difficult to implement, and it's very, very efficient. So you just explicitly implement this and maintain the canonicalization of the data structure. Basically, what that means is that whenever x is equal to y, whenever you observe this, pick one of them and go replace all the instances of one with the other in your data structure, and then do any deduplication that might result from that. Like I said, you have to make sure you collapse things if they become syntactically identical. Yes, please.
Back a couple of slides to the figure that you showed, the example. Is what you, yeah, this exactly. So is the following what you seem to be doing is you have G1 and G2 as being in an equivalence class.
Mm-hmm.
You replace them with the leader, means you replace them with one single node.
Yes.
So now F points to that node.
Yes.
And that node points to G1 and G2. The same is this with G3 and G4.
No, sorry. The canonicalization here would essentially just delete one of these, right? Because these are the same operator. I've only labeled the 1 and 2 just for our sake here, right? So if you canonicalized this, then this, let's start here. We have to pick a canonical representative for this class, and so all of a sudden now this G2 points to here, right? But G1 pointing to here and G2 pointing to here means that these are in fact syntactically identical. So we should deduplicate them.
Maybe it would help if you explain how did they end up in there in the first place? How did G1 and G2 end up in that same class in the first place, even though it's the same G?
Sure. It could have been the case that these were not equivalent to begin with, right? Someone built up a chain of G's somewhere, and someone built up a chain of G's elsewhere, and then some other identity, which we cannot see, equated them. And the thing that you have to do when you canonicalize is that whenever you get an equation, you need to make sure that this equation, the equation will violate canonicalization, right? Like every equation means that someone's leader is going to change, and you need to make sure that occurrences of that leader in your data structure get changed as well. So we arrived here because we didn't do that second part.
Topic of this nice figure here. So you mentioned that the exponential thing is that G1 can lead to G4 and G2 to G3.
Yes.
And the way in factorizations and ideas, you put an immediate node in between them. Mm-hmm. And then G1, G2 points to the node and the node to G3 and G4. And that I think where you describe the leader. So you actually replace the individual edges for representatives that we call leader that is found because all of them equivalent.
Yes.
And then you point to the leader, the leader points to them. So you factorize this graph by having an intermediate layer. I think that's the way you get around the n squared.
I think what you're describing is maybe a conceptually equivalent framing. What we actually would do is delete it, but we can discuss this more offline. All right. So yeah, the key thing that we need to do is actually just go in and poke around in the database, the eGraph, and change the values such that only canonical values are mentioned. This is the thing that massively shrinks the data structure. This is the thing that we're missing. So what do? Well, we canonicalize the database. All right, we could use a form of subsumption, and this is how the subsumption rule would sort of look. We'll just sort of skip past that. But let's just do what eGraphs do and actually implement congruence closure. What this means is that the equivalence relation is no longer explicit, right? Because it has to be super magical. Because when you add something to the equivalence relation, it's going to all of a sudden just do spooky action at a distance and change things in your databases. So all of our work that we did to join across the equivalence relations, well, now we can get rid of it. Because the database has been canonicalized with respect to this equivalence relation, the semantic quality becomes syntactic again, right? So whereas in our previous encoding, to join across these y's, we have to make sure that we join across this equivalence relation. We can actually write, again, just the y here. Because if someone had asserted this equivalence somewhere else, we would have gone and mucked with the database such that these two things became syntactically identical. All right, and so this is embodied in this tool that we built called Egglog. It's basically just a data log plus functional dependencies and this super magical extensible equality. I would like to look at these examples, but maybe we'll come back at the end. Oh, there's the web demo with all these nice examples. So maybe I'll come back to this at the end. But the key thing that I wanted to, maybe I'll just look at one of them. OK, so here is data. This is just a very simple example of what Datalog plus this sort of magical equality can get you. So this is just path reachability. Hopefully these rules are familiar. Edges are paths, and paths. This is just transit closure. Nothing fancy going on here. Here is our sort of IDB. We have an edge between 1 and 2, 2 and 3, and 5 and 6. Now, of course, if you sort of ran the program at this point, there would be no path from 1 to 6. But this is the sort of magical equivalence tuple. You can just say, hey, node 5 and node 3 become the same, right? That means these are identified and are now completely indistinguishable to the system, right? So all references to one of 3 or to one of these, it's not deterministic which, will be replaced by the other. So you can think about this as sort of, now you can answer sort of reachability queries where you're allowed to merge nodes and the sort of edges become combined as would be induced by like the equivalence relation over nodes. And in fact, this is, I don't know how to close this tab. Take a gamble here. All right, that was the right key. In fact, this is all it takes to give you equality saturation. So once you have just basically Datalog plus this extensible equality, you can do everything that you could have done with eGraphs and equality saturation. And in fact, it's much, much, much better. The implementation, and as someone who's implemented both of them, the implementation is much, much cleaner from the Datalog perspective. We can actually do actual query optimization now, so e-matching is considerably faster. One thing that has historically been a struggle for eGraph implementations are these so-called multi-patterns. So the sort of optimization example here is that, say you want to sort of co-apply these two rewrites. So you want to look for instances of A times B and instances of A times C where these are the same A. But these don't have, these can appear anywhere. There doesn't need to be any relationship between these two. And then you want to rewrite them to, we don't really have to get into what this is. This was very tricky because this steps outside of the tree-based paradigm that eGraphs were always in. But of course, you could write this in Datalog easy peasy by just having multiple stuff in your head. So no problem there. We also get incrementality, which was a whole research paper on how to do incremental e-matching. It just falls out for free. You just do semi-naive and you're done. So that's pretty slick. This, we sort of wrote this cheeky paper where we got 1,000,000x faster e-matching because these complex patterns are very, very cyclic. And so we just use worst case optimal join. So we're way asymptotically faster than the naive backtracking implementation that is conventionally used. So it's much faster. It's worth saying a couple things about functions inequality. Because when we talk about functional dependencies in a data log, or just what it means to be a function, that's sort of intrinsically linked to our notion of equality, right? Like that's what it means to be a function, is that if the inputs are equal, the output better be equal as well, right? And so how do we do that in a world where equality can be, changed at any given moment? So say you have some function f in your egglog program, and a function a function f where f of a is b and f of c is d. Well, what happens when the user decides willy-nilly, or for whatever reason, that a is equal to c, right? Like now you have an FD violation, and these can of course propagate up. These can sort of appear out of nowhere. F was never modified by the user here, and yet we have an FD violation. So what happens? This is very similar to like the Datalog with lattice implementations, where you have the final column is allowed to be some lattice value. You need to merge these according to some lattice laws. All right, sim rings also works with. Okay, so this is what we do in egglog. This is the technique that we use in egglog as well. We allow you, when you specify a function, you also have to give what's called a merge expression, which gives you the sort of the lattice law. This tells you what is the meat of the semi-lattice that is going to resolve any functional dependency violations. Right. So in this example, this is our goofy syntax for adding a tuple to the database. All right, so if you add foo of 7.5 and foo of 7.4, then of course the result is going to be foo of 7.4 because the lattice that we're in is the mid lattice. Easy peasy. Now, like I said, this also works for conflicts coming from equality. Well, we'll have to scoop open this again. We also use functions to work as constructors for our terms, right? These are the tables that you use to build trees of arithmetic expressions, if that's the domain that we're working in. These are functions, right? And so they need a merge expression as well, right? So what happens when this function mul, which is representing some constructor in our AST, experiences an FD violation? Well, this is sort of the magic, is the lattice that can be used to resolve this FD is in fact the mystical magical union operation, right? The way that we can resolve this FD violation is by asserting a new equality, which then of course then create other FD violations in some other table, right? And this is exactly congruence closure. This is happening right here. And while this works, and we have a proof of this in our paper, we do not have a good understanding of how this relates to the sort of lattice theory of Datalog, right? Because this is a sort of a dynamic operation, right? Like while it is sort of operationally behaving the same as, hey, just take the min or take the max or take the intersection, whatever, sort of standard lattice that you're in, this is a lattice that is sort of being built on the fly, corresponding to whatever the union find is happening under the hood. So I think that's an interesting algebraic question that we would like to look at going forward. And like I said, this is just congruence. The other thing to note is that when you resolve the existential variable, when you're creating these muls in the head of your rule, you need to come up with some sort of labeled null, right? Because you need to say, hey, in the head of our rule, say we're multiplying A and B, and that has never been seen before in our database, right? We need to come up with a new name, a new label null called AB. that we can that we can then down the road union with other things, right? So the way that these labeled moles in this dynamic lattice fit in with the sort of lattice theory of Datalog is again something we don't have a very clear picture of. Another interesting note is that the system that we built, and this is again sort of by coincidence, not by design, is that this has a very close relation to this column chase, right? We have EGDs, and we also, I mean, it's a Datalog, so we have TGDs. And I say it's closely related to this column chase because it's not, in fact, identical. And this is something Remy pointed out to us, is that because we are implementing the EGDs using this underlying union find, we avoid the sort of alternation property that some sort of operational views of the chase can have. Because when you take an EGD, you sort of have to pick one side and transform the database. But having this sort of persistent ambient union find prevents alternation, right? You can't alternate. You always have to go up in this union find lattice. So it's sort of an interesting observation. Okay, so just to quickly review, the good things about this spooky Datalog implementation is that it actually works, right? This allows us to implement equality saturation, which is a technique that people are really using in the programming language world, on top of something that looks pretty much like a Datalog. It has the fast congruence, so it has fast queries a la Datalog. It has fast congruence a la the sort of original eGraph implementation. In fact, it's the exact same algorithm. It's the congruence closure algorithm from like 1975. And it has these nice functions modulo equality, which, despite not really understanding how that they relate to the sort of lattice theory of Datalog, they do in fact work out. And this allows us to sort of get the E-class analysis system that we talked about before. The downside, and this is where definitely some future work is required, and hopefully this is somewhat interesting to this crowd, is that we've lost our ability to refer to specific terms, right? And this is actually somewhat important. The way that the egglog system works is by when you equate two things, it makes them indistinguishable, right? It is literally impossible in the system to ever distinguish between these two things again. And this makes it very fast, but there are situations where you might want to refer individually to terms within an equivalence class, and we've lost that ability here. Another way to think about it is we only have families of terms now. There's no such thing as an individual term. I've mentioned sort of this, some of the underlying semantic questions. And a big thing that I would like to work on going forward is that obviously this encoding that we just presented is limited to a single notion of equality, right? It's super duper specially baked in. What if you want to work with other relations of terms? Maybe it's two separate equivalence relations. Maybe you want to work with something that is a partial order, but not necessarily symmetric, right? Maybe you want to work with a sort of indexed equivalence relation. Maybe you want to do modular arithmetic, where you have equivalence mod 3, equivalence mod 10, or whatever, right? These are things that sort of the naive Datalog encoding would support, right? You just make another equivalence relation, you can write all those rules. But we've lost the ability to do that in this sort of performance system. All right, so I think I'll just stop there, and we can take some questions.
Thank you, Max. I think we have time for one or maybe two questions, but I would like to postpone the weightier questions for the discussion after Joyce. So please, Boris, you can, Christoph.
Who goes first?
Christoph.
Can you comment if you have thought about this? Does all this play well with magic sets? Have you thought about this?
Not only yes, but it will become essential.
You can think so, because all these additional help predicates that you introduced there, they should be interesting in this context, right?
So I think magic sets and the sort of demand transformation, which is sort of an extension of that, are going to be essential for controlling because termination is out the door, right? Because we have these TGDs, we're more or less doing the chase. And so the demand transformation I'm seeing in magic sets, I'm seeing as a way to sort of control the expansion of the database, right? If from the eGraph perspective, there's this mystical, magical eGraph that you're never going to reach that has all of the equivalences that you'll ever want. But if, for in the real world and you have to stop eventually, right? Now we're making a decision on, which equivalences are we, considering the juicy ones that we actually want to, find our optimized program in. And, any sort of tool that allows us to work with the control flow of Datalog, so it's magic sets, any sort of top-down demand transformation, I think is going to be essential to achieve that.
Boris, is that okay if you postpone your
Sure.
question?
Okay, so we're taking a break, but I'm going to hit you over the head with that bell in 25 to 27 minutes.